Awesome. Hopefully we can help you guys a little bit more with the homework. And today we're just going to talk about proofs and then some simple ones like direct proofs and then mathematical induction. Can everyone hear me? Actually, Nancy, can you hear me?
Yeah.
Okay, awesome. All right, we're going to start with the first one. Prove that the product of an odd integer and an even integer is always even. This should be simple enough. Any ideas how to do this? Where do we start?
We can define a variable like 2m plus 1 as the odd integer.
Okay, that's great. Okay, so prove the product of an odd integer. So basically we're given two things, right? Like an odd integer and an even integer, like you just said. Let me see. So like you just said, an odd integer. So an odd integer x can be defined as 2n plus 1. So basically we're saying there exists n in z, which is all integers, such that x is equal to 2n plus 1. And then we can also define an even integer, which is written as 2, let's say 2m. There exists m in z. So both of these are based on the definition of what's even, what's odd. So now what we want to show that xy is even, right? So that's what we want. So then that should be pretty simple, a direct proof. We have x and y, we just plug them in. So we have 2m plus 1 times 2m. That gives us 4mn plus 2m, right? Simple. And then because we want x and y to be even, and the definition of even is 2 times something, right? So then we just want to take a 2 out here. So we want this expression here to be something looking like this. So we take a 2 out and we get 2mn plus m. And since mn are both integers, we know by closure, this can be written as something like k. So then this is equal to 2k for some k in z, where k is equal to 2mn plus m. So that means x and y is even by definition, because 2k is even. So you can say since 2k is even, by definition, xy is always even. So this part right here is by closure property of integers. Any questions? Okay, let's keep going. That's simple now for the first one. Not too bad. Okay. The second one, use induction to prove that for each integer n is greater than 1, n squared minus n cubed minus n is divisible by 3. All right. So how does induction work? What do we start with?
We start to prove that the previous term satisfies this condition, is divisible by 3. And then from there we can prove this one. So like, yeah. All right.
So we start with the first case, right? We start with the base case. Yes, so someone said formulate Pn, yes, but then first of all, we need to start with base case. So induction is basically you prove base case, right? So base case first, and then after that, you have inductive hypothesis and then the inductive step. So then let's look at base case when, so since n is greater than or equal to 1, so the base case is n is equal to 1. That's the smallest that you can possibly get for n. So that means n cubed minus n is what? 1 minus 1 is 0, sure. And then this is divisible by 3. So 3 divides 0. So base case is check. Okay, so then we're going to go to the I don't know how actually. So I'm just going to write, so inductive hypothesis is that assume Pn is true, right? And then we want to show Pn plus 1 is true. So what is Pn in this case? So Pn is n cubed minus n. So let's actually write 3 divides n cubed minus n, right? So this is Pn. So what we want is Pn plus 1, which is 3 divides n plus 1 cubed minus n plus 1. Does that make sense? We just plugged in n plus 1 into the same formula. So now we get Pn plus 1. Okay, so how do we do this? What do we do now? So we want Pn plus 1. Okay, so this is just some simple algebra, not too bad. So Pn plus 1 is equal to n plus 1 cubed minus n plus 1, right? So this is what we have. So in the end, our goal is to write this in some kind of like, okay, let's not write k for now. Let's do like just 3 box. Like we want it to look something like this. If we're successful, then that means this right here is also divisible by 3. So what do we do? Algebra again. So we're just gonna open it up. We have 3n, so we have n cubed plus 3n squared plus 3n plus 1 minus n minus 1. First step. And then we're just gonna have n cubed minus, actually, yes, minus n. So remember that we have this right here. So we want this part to show up in our n plus 1 formula. So we basically what we want is for this part to be, for this n cubed minus n to be part of Pn plus 1 formula. So that's why we're going to move this minus n to the front. And then we're going to do the same thing. Just put the other stuff back here. And then the plus 1 and the minus 1 cancel out, right? So we have this. Yes, that is it. Someone asked, are we in the inductive step now? Yes, this is the inductive step. Inductive step. Okay, and then we have right here, we see that this is the same thing as Pn, right? Right here. So this is the same thing as Pn. And by inductive hypothesis, we know that, so you can say by inductive hypothesis, 3 divides Pn. So there exists let's say K in Z such that n, I'll plug it back in. So we have 3K plus 3n squared plus 3n. So now we can clearly see the goal in the end, it's still to get this part to look somewhat like 3 something, 3 times something. So now we can clearly see there's a 3 in every term. So we take it out, and then we get K plus n squared plus n. And still we know that n and k are both integers. So by closure property of integers, we can write this as, let's just say 3c, where c is equal to k plus n squared plus n. So now we conclude that we reached our goal successfully. So now we conclude that Pn plus 1 is also true. And that is QED. Can you draw a little box? I never do that, but anyway, just to do this for you guys.
Is it possible for you to scroll down a little?
I think you can just full screen, and you should see everything. I think it's like the difference between full screen and not full screen. Yeah, because this is like, did it work? Does it work?
I'll work on it.
Okay. Okay, next time I'll try to write on like a little bit, not at the most bottom of this. Any questions? I hope this made sense.
How do you know that you can substitute n cubed minus n for divisible by 3 if you haven't proven it yet?
But we assume that it's true, right? So look at the inductive hypothesis. We said assume Pn is true, and Pn is exactly 3 divides n cubed minus n. So this is kind of like a dominoes effect. If you think about induction, it's kind of like, oh, the first one is true. So it's kind of like, oh, I pushed the first little block or whatever. And then I assume that at some point in the middle of this sequence, like Pn is true. And we just need to know that Pn will help Pn plus 1 to be true. Then we know this dominance effect is going to keep going for like forever. So we know the statement is true for all n. So that's kind of what we're doing. So that's how we know we can substitute this Pn. So that's how we know that we can substitute this n cubed minus n to be divisible by 3, because we assumed it to be true. Like you have to have this step and then try to prove that the next thing is true.
Okay, so we know that the first one is true, so we're just trying to prove that the one right after is true with this, and then it keeps going.
So you need to know that the base case is true. So that's always the first thing, right? So basically the steps are like this. Base case is true. So you get the smallest possible number that you can find, like the smallest number that you find that to be true. And then you assume somewhere in the middle, like Pn is true. So n is somewhere in the middle. And then you try to prove that the next case is true. So n plus 1 is true.
Okay, so because we proved that n equals 1 is true, n plus 1 would be like proving n equals 2 is true, and so on and so on and so on.
Right, so that's the law. Yes, basically that's like that, because we proved that at some point at n is true, so you can move that n whenever you want, right? So this n could be n plus 100, then you know that n plus 100 n plus 101 is also true. So that's kind of the dominoes effect. Yes, you're correct. Wait, did someone ask a question? Oh, it does. Okay, this means divisible by like 3 divides. Okay, maybe next time I'll write words. If it is divisible by Pn where k is an integer. Wait, I don't understand the question. So okay, never mind. Any other questions? If not, we're gonna move on. No? Okay. All right, next one. Prove that if n is not divisible by 3, then n squared plus 2 is divisible by 3. So when you, I feel like, I don't know if this is true. I feel like this probably is for at least the proofs for the proofs that we're gonna do for this class. Like when you see something like not divisible by, this is like proof by cases. Because when it's not divisible by something, you get more than one possibility when it's not divisible by something. If it's like divisible by something, you only get one choice, is that 3 divides this thing. But if this number is not divisible by something, then you always get multiple cases. So like, what are the cases? What are the possibilities? What do we think? Yeah, someone just typed the answer in the chat. Great. Anyone else? Okay, so yeah, someone just typed the cases for us. So like, basically, there are 2 cases, right? So 2 cases. One is, so there are basically 2 types of remainders. The remainders of n are, are 1 or 2, right? Because if the remainder is 0, that means 3 divides n. And that's not what we want. We want 3 does not divide n. So that means the remainder has to be a 1 or 2. So let's look at case 1. When the remainder is 1, that means there exists, let's say k, sure, k in Z such that n is equal to 3k plus 1.
I think there's a question in the chat saying, will we ever use inductive proofs with proof by cases? I don't think so.
That's I don't think you would pretend. I don't think you would have to do it in this class. I mean, there could be proofs, I guess, that you might have to do that. Maybe like each case you have to prove inductively. That's possible. I guess like if you have like 2 cases and both cases you have to prove by induction, like that's possible. Or like one of the cases you have to prove by induction, the other is trivial or something like that. That's possible, but I don't think that could happen here. Generally, these proofs are nice enough. Okay, let's keep going. So we have n is equal to 3k plus 1. So then what we want is n squared plus 2 is divisible by 3, right? So still, we want the same thing. When it's divisible by 3, we want it to look something like 3 whatever, right? Okay, so then we have n squared plus 2. So that gives us, substituted in, 3k plus 1 squared plus 2. That is algebra again, 9k squared plus 6k plus 1. and then plus 2, right? And then we have 9k squared plus 6k plus 3. And that gives us 3k squared plus 2k plus 1. Because we take out the 3 because we want it to look like 3 something. So still, by closure property of integers, because we know k, like all of these things in here are integers, right? So then we can write this as 3c, where c is equal to 3k squared plus 2k plus 1 for some c in z. Now, case 1 is proved, since 3c is divisible by 3 by definition, right? So then we know that n squared plus 2 is divisible by 3 when the remainder of n is 1. All right, let's keep going. So we have case 2. So when the remainder is 2, we have there exists k in z such that n is equal to 3k plus 2. You can switch, honestly, like, I don't think it matters in this case. You can switch a variable if you really want to. But since it's a different case, like basically you're saying case 1 is done, I'm doing case 2, and this is like completely separate from case 1, using k is still okay generally. And it kind of makes it a little easier to look because you're not using so many variables. So now we're going to keep going, do the same thing. N squared plus 2 is 3k plus 2 squared plus 2. Algebra again, 9k squared plus 12k plus 4. Is that right? Yes. Okay. And then plus 2. And the same thing, 9k squared plus 12k plus 6. And then we take out a 3 again, 3k squared plus 4k plus 2. Any questions? This should be simple enough. It's the same exact thing, right? So by closure property of integers, we get this to be 3c again, where c is equal to this block right here. And by closure property, we know that c is an integer. And case 2 is proved also. So we're done. So that in the end, you can just say, like, I think generally proofs you can, like, it doesn't hurt to write words. So I guess it's like, it's very different from, let's say, if you take a calculus class or something, it's mostly just computation. I think a lot of proof-based classes, you do have to write a lot of words. And that's okay. Just make sure that the words that you write down are correct statements and they're logical from one step to another. Yeah, but I think like when you're trying to explain something, it is helpful when you actually write words. So in the end, we can just say that, you know, both case 1 and 2 are true. So then you can repeat the statement. If n is not divisible by 3, then n squared plus 2 is divisible by 3. So we're done. Happy face. Any questions? Okay. That's cool. That's not too hard. Okay, this one is about counterexamples. Shouldn't be too hard. describe, so state whether following statements are contrapositives of each other. So like, what does contrapositive mean? If we have, let's say if we have P implies Q, what is the contrapositive of P implies Q? Anyone?
Negation of Q implies negation of P.
Yes, exactly. So these are actually equivalent statements. Negation of Q implies negation of P. All right, so let's look at the two statements. If you like computers, you would love computer science. And the second statement is, if you do not like computers, you would not like computer science. Is this the contrapositive? True, not true?
No.
Yes. There are people typing in the chat as well saying no, not true. So what is this though? Does this statement have a type? Yeah, people said in the chat, it's the inverse. Yes, so this is the inverse. So inverse is not, so this is basically not P. You gonna cooperate? Okay, so this is basically not P implies not Q, and that is the inverse, not the contrapositive. So describe the traits a counterexample to each statement must have. So can we write the counterexample in some symbols like the contrapositive symbols? Like how would you write, like what would a counterexample be? If we have P implies Q for both of these statements, how would we write a counterexample? What would a counterexample look like? I see some answers in the chat. Yes, the counterexample should look like, so counterexample should look like P implies not Q, or P and not Q, right? Something like that. So can someone give me a counterexample of one? If you like computers, you would love computer science. What is the counterexample? What does the counterexample look like? Yes, okay, I see answers in the chat. You like computers, but you do not like computer science. Yes, that's exactly it. So the counterexample for the first one would be if you like computers, but you don't like computer science. All right, what about the second one? Okay, what about the second one? If you do not like computer science, you would not like, if you do not like computers, you would not like computer science. Yeah, someone just typed in the chat as well. Anyone else? Okay, people said I agree. Okay, so this person said you do not like computers, but you like computer science. Yes, great. Any questions? Not too bad. All right, we're going to keep going. So prove 7 is the only prime number that precedes a perfect square. So a hint is, how does the polynomial x cubed minus 1 factor? Okay, so this one is probably the harder one compared to all the other problems, but still not too bad. But let's think about, where do we start? So we want to choose a perfect square, not perfect square, perfect cube, right? And then the number precedes a perfect cube would be x cubed minus 1, right? That is the number precedes a perfect cube for some x. And we want to show that 7 is the only prime number that is in this form. So let's just use the hint. How does x cubed minus 1 factor? What do we think? How does the x cubed minus 1 factor? Any ideas? I'll give you another hint, is x minus 1 times something. It's not x squared plus 1. It's close. Nancy, do you actually know like an easier way of doing this other than doing long division?
I don't honestly. Probably just
Okay. Yeah, okay. And it's not x squared minus 2x plus 1. That is not true. Open it, open it and try it. Like it's not right. Yeah, but like, okay, I don't know if you guys learned this before, but this is how I've learned. At least for cubed factorization, for square, it's a lot easier. Yes, someone got the right answer. X squared plus x plus 1. Yeah, if anyone has like a easier way of doing this, like post on Piazza or something, so then everyone knows. But this is how I've learned. So you do like basically long division. You do x squared because then you get x cubed minus x squared, and then this is x squared minus 1, and then plus x, you get x squared minus x, and then x minus 1, you plus 1. And then you get 0. Like it's just long division. It's the same thing. But I'm not sure if there's an easier way, like a trick or something that you can do this with. But anyway. So you get x minus 1 times 1. Someone said, I think there are easier ways, but easily forgotten. So I guess it's not so easy anyway. But okay, but this is how it factors, right? So this is the first step that we're gonna go through to see that, to use the hint, if there's a hint, we're gonna use the hint. So what do we do now? We know that we want this to be a prime, right? We want this to be prime. So what are some properties of prime? So I think there are two things that we can do, but what are some properties of prime that we want to use here? Can anyone give me like, right, okay, someone said factor are 1 and n. Yes, exactly. So that is one very important property that we can use. I think there are two things that we can use. So prime, to be prime, first of all, factors are 1 in itself. So 1 and n, let's just call it n, or like, yeah. And then what's the other thing about primes? Can we have negative primes? Is that allowed? Like at least like not necessarily allowed, but like the definition of it, the definition of primes says that prime has to be basically greater than 1. So these are the two properties of prime that we can use here. So I think it can go either way. So if we look at the first one first, so let's say that we use the first property of prime first. The factors are 1 and n, right? So we factored n cubed to be these two things. So we know that one of them has to be 1 for this x cubed minus 1 to be prime. One of them has to be 1. If one of them is not 1, then this number is not prime, right? So one of them has to be 1. So what are the two possible cases? Either x minus 1 is 1, or x squared plus, oh, no, not 0, 1. One of these two cases has to be true, right? So we're just going to do some algebra right here. So this makes x equal to 2 when x equal to 2, x cubed minus 1 is 7. So that's 8 minus 1 is 7. And 7 is a prime. But then right here we have x squared plus x, this is 0. So we have x plus 1, that's 0. So this is just simple algebra, right? So either x is 0 or x plus 1 is 0. So we have x is negative 1. So in either of these cases, x cubed minus 1, this becomes negative 1. And this becomes negative 2. Neither of these cases, x cubed minus 1 is prime. So these not prime. Right? Is prime is when it's 7. This is the only time. There's no other time that this form can be a prime. So this is the first way that we can do this. And there's also another way. Let's say, so we have the same thing, x cubed minus 1. We factor it again. Oh, first of all, any questions about this first part of the proof? Does this make sense? We just use the property of prime. Okay, we're gonna do the other way. So we're gonna use the second property of prime, which says the a prime number has to be greater than 1, right? Since x cubed minus 1 is prime, so that means this is greater than 1. So okay, let me write a more formal way. So how can we do this? So okay, you don't want to go? Okay, fine. Since prime numbers are greater than 1, we know that x cubed minus 1 is greater than 1. So x is greater than 1. Is that simple enough to see? I mean, you can move it to the right and then and figure it out. But just do some simple algebra. So we have x is greater than 1. So then we're just gonna start plugging in numbers. So the smallest case is when x is equal to 2, right? When x is equal to 2, x cubed minus 1 is 7, which is a prime. And then we continue to argue for For larger numbers of x, so if we keep growing x, so like if we say x is equal to 3, x is equal to 4, we can always factor x cubed minus 1 from the formula above So this means that when we have, so basically this is saying x cubed minus 1 is equal to the formula above, right? So if we increase the value of x, so let's say when x is equal to 3, the first part will become a 2. And when that happens, we already know this is not a prime number. And then if you keep growing, x is equal to 4, then x minus 1, that's 3, right? So you can always have 2 times something or 3 times something, and then it continues to grow. So that means x cubed minus 1 is not a prime anymore. And since x is greater than 2, x minus 1 is greater than 1. So this basically violates the property, the first property of prime numbers, which is that the factors have to be 1 and n, because we have a factor that is not 1 and n, right? We have something else factoring out of this number. We have shown that x cubed minus 1 has factors other than 1 and itself for all x greater than 2. Therefore, the only time x cubed minus 1 is prime is when x is equal to 2 and x cubed minus 1 is 7.
So this is just a second way to prove it, right?
Yes. Yes.
Okay. Looks like the previous one is easier.
Yeah. I mean, people think differently, right? Like some people think that maybe one way is easier than the other, and there are always different ways to prove things. So someone asked if we have time, can we go over the first part? Like, which is the first part? Like the first part, you mean the first proof or the first part of this proof? The first way to prove it. Okay, yeah, sure, in a second. But let's finish this one. Can we explain how you know to use n cubed minus 1 to prove this, or how you would deduce to use this in this proof? Yes, because it says proof 7 is the only, okay, go back to the problem prompt. 7 is the only prime number that precedes a perfect square, right? So this is the key, right? So precedes a perfect square. So perfect square is this, right? For some x in z. That's perfect square. The number precedes perfect square. The number before the perfect square would be in this form, always. So this is what we want. Like this is something, this is like the kind of the key to start the problem, is to know that a perfect square, the number precedes a perfect square, will always be in this form. And then when we talk about prime numbers, the first thing you should think about is how to factor something. it's a prime, right? I mean, we don't really know anything else about primes at this point. There are lots of properties about prime numbers, but right now we only know that prime has these two properties, is either greater than 1 or factors are 1 in itself. Proofs are generally just using what we know already to prove something we don't know, right? So like, just think about what's given in the problem prompt. Does that answer your question? Hopefully. Any other questions? We have 4 minutes. Okay, there's this one last one that is simple. So if someone can give me an answer, that would be great. Write the following sequence as a recurrence relation with sufficient initial values specified. We all know what recurrence relation is. So we want to write dn to be dn minus 1 and do something else, right? Dn minus 1 plus something, or something like that. Yeah, so basically we want to write this as a recursive formula. So we have this thing, and then we want to write this. This is a closed form, right? Because it has like n in it. So we want to write this as in dn is equal to dn minus 1 something. So how do we do this? We can write the first few terms, right? So d1 is equal to 1 over 1, 3, right? So that's d1. And d2 would just be the first two terms, 1, 3, plus 1 over 3, 5, right? So that's second term. D3 just keeps going, right? So we realize this part is just D2, right? And if you keep going, it just keeps going. But this part is just D2. So then D3 is just D2 plus 1 over 5 times 7. And how do we write 5 times 7 in terms of n? It's actually written in a formula already. It's just this. Right? So we get dn minus 1 plus 1 over 2n minus 1, 2n plus 1. That is it. Yes, very good. Somebody typed the answer in. I see in the chat. Make sense? Any questions? No? So quiet today. All right, that's all. If you have questions, you can ask last minute questions, but if not, have a good one, guys.
Yeah.
Good luck.
Do you have
Go ahead.
you have extra little time? I just have a question in the homework.
Oh, you should go to office
Like the
hours.
question on the
Because I don't, yeah, please go to office hours for homework questions, because there are students who maybe haven't tried it yet, and it's not nice to review the answers or whatever.